All right, let's get started on our last section of this mini unit on basically our extrema, what's happening in a graph, our extrema, and now we're going to learn about the inflection points. So our last section in this little unit that we're doing. So first, let's do a quick review of our first derivative. So what we've learned so far in the last two sections that we've done. So first section we did, which was 3.1, we went over what does setting the first derivative equal to 0 give us. So in case you forgot what that means, setting the first equation or first derivative equal to 0 and solving for x is going to give us the critical values. Now, what are the critical values? Well, the critical values, if you remember, could be the extrema. So they could be the absolute max, absolute min, or relative max, relative min. So when we set the first derivative equal to 0, we get the critical values, which are our potential maxes and mins. Then the second day on section 3.3, we went over what does the first derivative test. So we didn't actually call it the first derivative test, but what does the first derivative tell us if we find the critical values? So remember, we found the critical values. We had an open interval this time. We didn't have a set interval. And we plugged in values on either side of the critical point. What did that tell us? Like, how did we analyze it? So if you remember, what we analyzed was whether the function was increasing or decreasing. So what we did here was we plugged it in on either side, and then we looked for the different portions that we had, like the ranges or the ranges of the domain in a certain interval. So like from infinity to 4, 4 to 3, 3 to negative infinity, and we determined how was that function moving? Was it increasing or decreasing? So we determined how the function was increasing or decreasing. Okay, so all these things are going to be important. I would strongly suggest that you put these in your notes. Remember that your quiz, we are still having a quiz coming up on Friday, and it is going to be, you're going to get to use these notes. So I would definitely write these down. There are going to be some conceptual questions on there. So now let's look at what we're going to do today with the second derivative. Okay, so I'm going to give you a second to write these down, the steps. I would give yourself some space. We're going to do two examples on what the second derivative is going to tell us. So the good thing is I could have us go through the entire first derivative, graph everything, and then move forward with the second derivative. Due to time, I'm going to have us just go over what the second derivative tells us and then do some testing of these points. And we're going to do kind of a fake graph like we did earlier. So if you need to pause, go ahead and pause. You can write these steps down, but I'm going to go ahead and do an example just right away, and we'll follow these steps. Okay, so example number 1, we're going to have as y equals 1/3, and you'll see why it's a fraction. It's not that bad, I promise. 1/3 x to the third plus 2x squared minus 5x minus 6. Thanks, Pippin, for joining us. Okay, so first thing we're going to do is we're going to find the second derivative. So in order to do that, we have to find the first, right? So we're going to start with just doing the first derivative here. So I multiply 3 times a third, which then cancels out, which is why I told you it wasn't so bad. So we'll have x squared plus 4x minus 5. All right, now I need to find the second derivative, so I'm going to go ahead and do that right away. So y prime prime is going to give me 2x. There's an x up there. Sorry, that should be 4x plus 4. Okay, so I found my second derivative. So step number 1 is done. All right, the next step then is to set them equal to 0 and solve for x. So I'm just going to set this equal to 0. I'm going to kind of do this in my head, but so I'm going to subtract 4 on both sides. So that'll give me 2x equals -4. And then I'll divide by 2, and that'll give me x equals -2. So this right here, if you read, what this is this gives us a potential inflection point. So what does the second derivative tell us? Well, it tells us our potential inflection points. So to recap, the first derivative tells us our potential maxes and mins, our critical values. The second derivative is going to tell us our inflection points. So this is a potential inflection point, but we need to test to see if it is a true inflection point. So what we do is we're going to plug this back. Well, first we'll start by finding what is this exact inflection point. So we can plug this back into the original up here, and I can give you a second to do that to double check my work. But when you plug it back in, you're going to get a decimal. I ended up getting 9 1/3. Okay, 9 1/3 or 9.33 repeating. So this is our potential inflection point right here. So now what we're gonna do is we're gonna test to actually determine if this is an inflection point and determine the concavity. So I know we didn't get into like what the concavity was, but just to understand the concavity, if you want to draw this example. So this would be a concave down. Okay, concave down would be like this because it's going downward. And so anything here, so like, for example, if I had this function like this, okay, this would be, my inflection point would be right in there because the inflection point is where it changes the slope of the function. That's what an inflection point does, or the concavity and inflection point. So it changes the concavity. And so you can see here from this, I'll highlight it in a different color. So from the inflection point downwards, this is a concave down for the function. And then this piece here would be a concave up after the inflection point. So what we're going to do is test on either side of this inflection point to see, is it concave up or is it concave down on either side of our inflection point that we have? Or maybe it's both. So this would be considered a concave up. And if this was the inflection point that we found, the concavity doesn't change because this is concave up and this is also concave up. So what we're going to do is we're going to test to determine what's happening on either side of this point, because this inflection point could in fact be a disguised max or min. So that's what we're going to do now, is to test that. So just so you understand, concave down is here, concave up is here. This one represents concave up and concave down. Okay, so how do we test these values into our, how do we use the second derivative? So what we're going to do is we're going to take this value, -2. And so we did this before, if you remember back before Christmas, just on like a number line. And so we have this inflection point of -2 here. So we're going to test a value to the right on the number line and to the left on the number line to determine what's happening. So what I'm going to do is, I just like the number 0 because when you plug in 0, it's so easy to determine it. And then when I plug in, let's see, a negative, I'll just go with -3. So I'm also going to plug in -3 to see what's happening on the left side of this inflection point. Now, the key is when you test these values, you are plugging them into the second derivative. So we're going to be plugging these two values that we chose 0, -3 into the second derivative. So if I plug in 0 in here, it'd be 2 times 0 is 0 plus 4. So it means that I'm going to get a +4. So that means that anything that I plug in to the right of this value, to the right of -2, is going to give me a positive answer. That means that it is concave up right here. So that means in this situation, I'm going to have a concave up. Okay. And so from -2 beyond, so basically what you would write when x is greater than -2, I'm going to equal, or it's going to be concave up. Okay, so that's what you would write as your answer, because they're going to ask you to test the concavity. And so you're going to say x, when x is greater than -2, you are concave up. So now we got to check the concavity to the left. So if I plug in -3, I'll get 2 times -3 is -6. -6 plus 4 will give me -2. So anything to the left, these are all going to be negative values, which means that over here, my function is going to be concave down. So that means from x, anything less than -2, I'm going to be concave down. So this is a true inflection point, and you may want to write this down. This is a true inflection point because the concavity changes on either side. So if we were to plug these in and they were both positive on either side, that would mean that this is actually going to be either a max or a min. But this is a true inflection point because the concavity changes on either side, which means that the slope changes of the function to a positive and a negative. Okay, so this is all we're doing here. Basically, we are finding the second derivative, we're finding the inflection point, and then we're determining, is this a true inflection point, and testing the concavity on either side. And then writing here, the final answer is writing what is the concavity in relationship to the inflection point or points that you find. Okay, let's try another one. This time I'm going to have one that has more than 2 inflection points to see what that looks like. Okay, so example number 2. Let's do, we're going to do x to the 4th now. So let's do negative. So we'll do y equals negative x to the 4th over 2. And then plus 4x to the 3rd plus 15x squared plus 2x plus 1. Okay, now if you want to go ahead and pause this and you want to try to go ahead and find the inflection points without me, feel free to do that. So I'm going to go ahead. I know I don't have the rules on here, but you should have them written down. So the first step or the first rule is we need to find the second derivative, but we obviously have to find the first before we can find the second. So first derivative is going to be, so if I multiply this here, it'd be negative 4x over 2, which is negative 2x to the 3rd. And then plus 12x squared plus 30x plus 2. Okay, let's keep going. And I got to find the second derivative now. So my second derivative is going to give me negative 6x squared plus 24x plus 30. All right, now you're probably thinking like, oh God, this is like, how am I going to solve this, right? So yeah, we would have to factor. I'm going to caution that we don't have to do SMRF. You might look at it and say, oh, we have to do SMRF. Remember, the first step in SMRF is to GCF. So let's GCF. And I can take out a 6. These all have a 6 in common. I'm actually going to take out a negative because I don't want my leading term to be negative. So I'm going to take out a negative 6. And that'll leave me with 6x. And then I got to change this sign, minus 4x minus 5. Okay, because remember, I need my first step or second step is to solve for x. So I have to set the second derivative equal to 0 and solve for x. Okay, now this negative 6 is insignificant because there's not an x with it. I'm more concerned now about this piece. So if I set that equal to 0, I'm going to have to factor. I'm going to ask myself what multiplies to be negative 5 and adds to be negative 4. Your two numbers would be negative 5 and a positive 1. Okay, because if I multiply those together, I get negative 5. If I add them, I get a negative 4. And then I'll have my x values will be, if I set those equal to 0, I'll have x is 5 and x is negative 1. Okay, so these are our potential critical values. Now, you can do this now or you can do this later, it doesn't matter, but we're going to need to plug these back into the original at some point to find what is the exact critical value. So you can do that now or later, it doesn't matter. Well, not critical value, these are inflection points. So remember, critical values are derivative, inflection points are your second derivative. So we're going to have to actually plug these in eventually to find that. I will go ahead and do that now and tell you what the answers are. So if you plug in 5, you end up getting, it is a huge number. I got 573.5. So yeah, that is a big number, 573.5. And for negative 1, I got 9.5. Okay, so those are the exact x comma y values for the inflection points, if they are inflection points. Okay, so now we're going to go on a number line here. So my potential inflection points, I have a -1 and I have 5. So now I have 3 different intervals that I have to test in. I have to test something that is to the left of -1. I have to test something in between -1 and 5, and then something to the right or greater than 5. So I have to test 3 different points into my second derivative, which is here. Okay, so let's pick, again, I like to pick easy numbers. Let's go with 0 because that's an easy number to pick. So I'm going to pick 0. I'm going to go with -2 because that's the next highest one. And then I'll go with 6 over here. All right, so I'm going to start with 0 because that's the easiest one to plug in. So if I plug in 0 into the second derivative here, everything cancels, then I'm left with 30. So that means since I'm left with 30, a positive 30, all the numbers, any number that I were to plug in between -1 and 5 are going to be a positive value, which means that from -1 to 5, I am concave up. Okay, so that is one of our, so from -1, we can do this, -1, so that would be less than X. Wait, did I do it right? Yeah. And then greater than, no, less than 5, other way around, less than 5, sorry, greater than -1 is going to be concave up. I'm just going to abbreviate concave up. Okay, so it should look like this. Sorry about all that scribbling. So greater than -1, but less than 5. All right, now we can plug in -2. So I plug in -2 here. You can go ahead and do that. What I ended up getting was a negative, I think a -18 or no, it was bigger than that. But I ended up getting a negative value over here. Okay, so that means everything when X is less than -1, I am concave down. Okay, so that means over here, I'm going to be concave down. And then now I need to test 6. So if I put 6 in, it's a pretty big number again, but you end up getting a negative over here. So that means over on this side, again, we are concave down. So anytime X is greater than 5, then I'm going to be concave down. So the last thing we just want to ask ourselves is, does the concavity change between every inflection point? So here it went from down to up to down. So since this changed, yes, these are both inflection points. Okay, so they both are inflection points. Now on your homework, you will find one where it doesn't change. So look out for that, and then we'll talk about that in class. Okay, so that is the first part of what the second derivative can do for us. There's one more thing I want to show you about what the second derivative can do for us. Okay, the second derivative test. So now the second derivative test is where we can determine if we have relative extrema, a max or a min, using the second derivative test. So instead of using the first derivative, how can we use the second derivative to determine if we have a max or a min? So again, if you want to pause this, we have some steps we're going to go through. And also down here in the black text are the rules. So if you want to take a moment to copy that down, pause me. I'm going to get going though, but you can stop at any time and go ahead and write that down. All right, let's get into an example right away. All right, so our example is going to be, I'm going to do 2 just so you can see the different ways that you might see it. Okay, so we're going to do the function. So y equals 5 plus 3x squared minus x to the third. All right, so in these problems, what they're going to be asking is they're going to ask you to determine the relative extrema using the second derivative test. Now, could you do this using the first derivative? Absolutely. But they want you to see that there's another way to do it. Maybe you like this way better, maybe this is faster. On the quiz, I'm going to have you do both. So you'll have to find the extrema using the first derivative and then this other method using the second derivative test. So the first step is to find the critical points, which we've already learned how to do. Remember the derivative of the first derivative, find them, set equal to 0, solve for x. So that is how we find the critical values from the first derivative. So if I do that, I end up getting, so first derivative gives me, derivative of 5 is 0, so then I'll get 6x minus 3x squared. Okay, so now I set equal to 0. I'm going to have to factor this, but this one isn't so bad. We have a GCF here. We can take out a 3 and an x. So I'm going to take out a 3x. And I'll be left with 2 minus x. All right, then I have to set 3x equal to 0, which 3x equal to 0 is just going to give me the x is 0. And then when I set 2 minus x equal to 0, what I could do is I could just add the x over, and then I would get x equals 2. I mean, you could subtract the 2, but then you'll have to divide by a negative, which switches it back to a positive 2. Okay, so these are my two critical values, and I'm abbreviating these as CV. So these are my two critical values, and that's what I use down here in the rules. So critical values. Okay, now we're going to find the second derivative, and then we're going to see how the second derivative can help us determine if these are max or mins. So the second derivative of this function would be 6 minus 6x. All right, now we don't have to set this equal to 0. We're not worried about inflection points because that's not what we're worried about. We're worried about determining if these critical values are actually extrema using this derivative. So now we're going to take our two critical values and we're going to plug these, so 0 and 2, we're going to plug these into our second derivative. Okay, so let's do that and let's see what happens. So if I plug in, I'm going to make this y prime of 0. So if I plug in 0 into this function, I'm going to get 6 minus 0, which is 6. Okay, if I plug in 2 into this function, into the second derivative, I'll get 6 minus 12, which is negative 6. So now what we do once we plug them in here is we're going to make a conclusion based on these rules. So if we were to end up getting 0 when we plugged these in, that would mean it is inconclusive. We can't tell by the second derivative test what this is. It could be an inflection point, it could be a max or min, but we can't tell. So if it's 0, it means that you would need to do further investigation, which I'm not going to have you do. So if it turns out to be 0, you can just write inconclusive and leave it at that. Now, if the value is greater than 0, so in this case, this one was greater than 0 right here. The 6 was greater than 0. So if it's greater than 0, that means that at 0, we have a relative min. So this will be a relative minimum. Now, why you're thinking, is it a relative minimum? Because it's a positive value. Well, what this means is that the 6 means actually that this is concave up. So if it's positive, remember when you plug in numbers into the second derivative, it tells the concavity. So if the concavity is concave up, that means that function looks like this at that point, which gives you a relative minimum in the big scheme of the function. So it's the opposite of what you think it is. And then the same thing happens here. If it's less than 0, which is this point, negative 6, that means, remember, the concavity is what the second derivative tells us. So that means the concavity is negative, which means the concavity is downwards, which gives us a maximum point at that particular value. So this would be a relative max. Now, we don't know if it's the absolute or not. Doesn't matter. We're not concerned. We're just trying to figure out, could this be a maximum or minimum point based on the second derivative? Okay, so that is what we're doing. That's all we're doing. Find the critical points, find the second derivative, plug those critical points into the second derivative, and then determine would those be max, mins, or inconclusive. All right, I'm going to try one more. If you feel like, yep, we got this, you can kind of fast forward through, but I'm going to show you one more just in case you are confused or you might need a little bit more help with any of these. Okay, let's go to the next page. And again, if you want to, if you're like, yeah, I got this, I'm gonna move on, that is fine. But I'm gonna show you one more. I'll show you one more just that has 3 values in it. So I'm gonna do y equals x to the 4th minus 2x squared plus 3. Okay, so rules. First thing is we need to find the critical values. So we'll set or find the first derivative, which gives me 4x to the 3rd minus 4x. Okay, lucky us, this one is a GCF. I'm gonna set it equal to 0, so I'm gonna take out a 4x. And that's gonna give me x squared minus 1. Okay, this is a double factoring one now, so because this here in the parentheses, we are concerned with the 4x because there's an x out there. So 4x equals 0. It will give me 1 critical value at 0, because if I divide by 4, I get 0. Now, there's 2 ways we could handle this one. You could set this one equal to 0. You could add the 1, which gives you x squared equals 1, and then take the square root on both sides, just remembering that x is both, there's 2 values, so x is positive and negative 1. So as long as you remember that, you're good to go. Another way you could think about this is you could factor this. If you factored this, it would be x plus 1, x minus 1, which still gives you the values of x equals positive and negative 1. So either way could work on solving this for your critical values. So we have 3 critical values now. And what we'll do is we'll plug those in, but we got to find the second derivative next. So the second derivative, yep, let's use yellow. Green Bay Packers, let's go. So it'll be 12x squared minus 4 will be your second derivative. Okay, so now we have to plug in 3 values. So we're going to plug in the function at 0. Okay, we have to plug in the function at 1. And remember, we're plugging it into the second derivative and the function at negative 1. Okay, so if you want to do that, go ahead. I will do that in my head. So if I plug in 0 into here, that one's going to cancel and I'm left with a negative 4. If I plug in a 1, 1 squared is 1 times 12 is 12. 12 minus 4 gives me an 8. If I plug in negative 1, I'm going to get still a 1. 1 times 12 is 12, minus 4 is still 8. So 1 and negative 1 gives me the same value, doesn't matter. Okay, so what does this tell us? Now you can go back to the rules and look, but it tells us that if I have a negative, it is a, remember that means it's concave down. So that means I have a maximum. So this is going to be a relative max. And if I have a positive value, that means that it's concave up, which means these two are both relative mins. Okay, so that's all we're doing here in our second derivative test is we are using our second derivative to help us determine if I have a relative max or relative min, using the idea of concavity. Okay, so that was it. Those were the 2 parts of the second derivative. So lastly is your homework problem. So page 193, that was the first 2 problems we did. So where you're just determining the concavity. And page 192 are the last 2 we just did where you're using the second derivative test to determine if you have a relative max or relative min. Okay, come to class tomorrow with all of this work and we will go over things together. All right, let me know if you have any questions.